So we are back again. We are now talking about quadratic functions, and SOC means second order conditions. That is the second order conditions on the second derivative. That is the conditions on the second derivative which will guarantee that my critical point, or a point which satisfies f dash x star equal to 0, is a maximizer or minimizer. We will see that that kind of condition on the second derivatives is very logical, and that can be motivated through studying the minimization of a quadratic function. Let us now look at this quadratic function qx equal to ax square plus bx plus c. You have heard about linear functions, you have heard about quadratic functions. Quadratic functions are known to you from your school days because you have studied quadratic equation. When you put qx equal to 0, you are studying quadratic equation. Now in this particular case, I am choosing a to be strictly greater than 0. Okay, just I am choosing a to be strictly greater than 0. Now if I want to find a minimizer, as a first step, what I do is take the derivative of qx. So q dash x is twice of ax plus b. C is a constant. So which means if I put qx equal to 0, the only x star which satisfies this is minus b by 2a. I can write this solution because I know a is strictly bigger than 0. There is no other point on Rn on R which will satisfy 2ax plus b equal to 0 or q dash x equal to 0. There is only one critical point. So we have to now decide, is this point a minimizer or a maximizer? So first let us find the objective or the functional value of qx at x star. So q of minus b by 2a, if you compute it, it will become minus b square by 4a plus c. Now the interesting fact is that you will observe here that ax square plus bx plus b square by 4a, which is this term, here. So ax square plus bx plus b square by 4a is equal to 2ax plus b whole square divided by 4a. A is obviously strictly bigger than 0. This is greater than equal to 0. Now observe that 2ax plus b whole square is strictly greater than 0 for all x which is not equal to x star, because only when x star is minus b by 2a, 2ax plus b, which is nothing but the derivative, that is equal to 0. So when x is not equal to x star, I can write ax square plus bx plus 4b square by 4a is strictly bigger than 0, or ax square plus bx is strictly bigger than minus b square by 4a, or ax square plus bx plus c is strictly bigger than minus b square by 4a plus c. Now in this case, what we are getting, and this is true for all x in R which is not equal to that particular x star minus b by 2a. So here what we get is actually a global minimizer, that is x star equal to minus ba is a global minimizer, but has this interesting property that when a is strictly bigger than 0, x star minus ba is not only a global minimizer for the quadratic function, it has this property that when x is not equal to minus b by 2a, ax square plus bx plus c, that is q of x, is strictly bigger than q of x star, strictly bigger than. This is a very interesting property. There is no other x for which those values would be equal. Now what is a in this case? What is a? A greater than 0, what does it signify? If you take the second derivative of the quadratic function qx, then a second derivative is nothing but 2 of a, because q dash x is 2ax plus b, so second derivative is 2 of a. And as a result of that, if a is greater than 0, 2a is greater than 0. So, or if you say 2a is greater than 0, then a is greater than 0. And that would lead to the fact that x star is a minimizer. So, the second derivative condition, with a greater than 0, the second derivative condition is embedded in this. because that means 2a is greater than 0. So the second derivative is greater than 0. So the second derivative being greater than 0 is leading to the fact that the critical point, that is the point where f dash phi dash q dash x is equal to 0, is actually the minimizer. So the second derivative condition actually makes sense, and the quadratic function allows us to make that justification. Now suppose I can give a very nice proof using Taylor's theorem for the general differentiable function, but I'll not do that for functions from R to R. I'll finally do that for functions from Rn to R, but I'll not do that here, but I'll give you a kind of motivation as to what happens around as to what happens around a local minimizer. And also I'll first discuss this interesting property, that is qx is strictly bigger than qx star when x is not equal to x star. So this allows us to introduce something called a strict local minimizer, and this idea is not just something I just saw something and I have introduced something. It has a meaning and it is required specifically for actual computation, and you will see why. So you have understood what I'll talk about, what I will call a strict minimizer. The strict local minimizer is a point for which I can find a neighborhood of x star, that is x star minus delta and x star plus delta, this delta neighborhood of x star, so that any x which is there but not equal to x star, right? So I should have made, there is a small mistake here, should be for all x not equal to, there is a little mistake in the definition. It should be for all x in this but not equal to x star, x not equal to x star. So that has to be mentioned, which I had forgotten to mention, so kindly forgive me on this. So it is actually mentioned in the final notes which will come to you. So a strict minimizer is one for which fx is strictly bigger than fx star for all x not equal to x star. So all x, it should be all x not equal to x star, but x is within this neighborhood. So what happens to the definition of the strict, why we need this? For example, you take this function. If you draw this function, it is like an inverted tub with king points at -1 and +1, turning points. And this function was first given in a book by the legendary optimizer who is called the Wizard of Optimization, Roger Fletcher, in his book Practical Methods of Optimization, which was published by Wiley in 1987. This function is interesting because if you go by the definition of local minimizer, you can easily show that x equal to 0 is a local minimizer of this function. But if you actually draw the function, you would realize that x equal to 0 is a global maximizer. Okay. So how to distinguish between these two? You observe that its real intrinsic property is that x equal to 0 is a global maximizer and not a local minimizer. But by definition of a local minimizer, it is local minimizer because the function actually rises up from the negative side at -1 to +1, it becomes 0, and again goes down on the goes down after x equal to 1. So x equal to 0, if you take a small neighborhood, say -half +half around 0, then for all x there, fx is equal to 0. So naturally that it satisfies the definition of a local minimizer. But in reality it is a global maximizer because the function value is all of these function values are less than equal to 0. Right. So when you so how I have computed this function? Look, this function is an interesting function. This function will not have a derivative say at -1 and +1. So what happens? What I do, I plug in the value of x. When you take any x, say take x equal to 1, I plug in the value of x. So it is 1 minus 1 is 0, 1 plus 1 is 2. So what is the minimum of all these three values? 0. So it's 0. So put half. So it is 1 minus half is half. It is 0. 1 plus half is 3 by 2. What is the minimum of these two values? 0. So the minimum. So you plug in an x and compute these three functions 1 minus x, 0 and 1 plus x. Find the minimum of these three and that will be the value. So x equal to 0 becomes a global maximizer here, right? You can immediately understand the x equal to 0 is a global maximizer, but by definition it is also local minimizer. To avoid such kind of things, we introduce what is called the strict local minimizer or strict local maximizer. For example, if you draw the graph of the parabola fx equal to x square at x equal to 0, f0 is 0, but when x is not equal to 0, f0 is positive. So 0 is a strict local minimizer. So introducing that strict property, you eliminate these kind of anomalies. Now you come to the second order condition and we want to motivate it for a general function. We are not going to prove it. Please understand that here we are not going to make any proof. Proof would be for functions from Rn to R. So let's take your knowledge of math 101 and write down the second order Taylor's expansion, assuming that the function is twice continuously differentiable. We are not assuming it is thrice continuously differentiable. Second order Taylor expansion means that around x star, a function which is represented by a curve can be actually approximated by a quadratic function. So the value of f of x star plus h can be approximated by a quadratic function. If you can put a cubic function here, that is like a third derivative, it will be a better approximation. So it approximates the graph of the function, the curvature of the curve better. So for us, let us just talk about the quadratic function. So the Taylor's expansion. So f of x star plus h is this f of x star plus f dash x star h plus 1 by 2 factorial, which is half, f double dash x star into h square plus the error term small o of h square, that when h goes to 0 or h, so h square goes to 0. So when h square goes to 0, OH square goes to 0 faster than h square, which is means pretty fast. So I can write this as phi h plus OH square. So this part I am taking this part. So if you forget this OH square, if you cut it off, f of x star plus f dash x star h plus half f double dash x star h square is actually a quadratic function in h square. So the interesting part is that can I talk about the minimizer of the quadratic function, which we already know, and try to, and you know under what condition I have found a minimizer, because you see for the quadratic function, if I had put a strictly less than 0, the same point would become a maximizer. So the critical point, the point where f dash x star equal or q dash x star equal to 0 is a maximizer or minimizer depending on the sign of a, that is the sign of the second derivative. So please understand that the second derivative lies in this quadratic approximation part. This phi of h is called the quadratic approximation of f at h. So this is a quadratic function of h, and this minimization of this quadratic function is the key to our understanding of the second order condition, second order sufficiency condition, that okay, if f double dash star x star is strictly bigger than 0, I will get I'll get a local minimizer. So you can understand that f double dash x star is actually now associated with the quadratic function phi h. So if I can speak about the minimization of the quadratic function that we had just learned and the conditions that we have just imposed there, we will get what we will get the conditions that we require for the function f. Now you might ask that, okay, you have just very cleverly taken off that error term, as if there is no error, forget it. Of course, if f was a quadratic function itself, then there would have been no error term, because that's the exact expansion. But if it is because it's not a quadratic function, there is an error. So that we have to take care of that error, because we know that in this case, if I just want to minimize the quadratic function phi h, the only thing I have to know that a, that is half of f double dash f x star, must be strictly bigger than 0. Then I will know that and if x star is a critical point, then so if this is a, and if h is a critical point, then if half of f double dash x star is strictly bigger than 0, which is same as f double dash x star is strictly bigger than 0, then we will at any critical point we will obtain the minimizer. So the ax square plus bx plus c model can be applied here, but here the a is nothing but half of f double dash x star. So what we do now, we take a more careful look at it, because we have to be careful about this error term. What we will say, we are not proving anything here, we are trying to motivate. So we are now trying to say that let us assume that the quadratic function is so nice that it locally underestimates the function phi at x star. Means, you know that the function h, the function phi of h is a function of h, right? And you know, let the function, let us look at the function phi at 0. If I put h to be 0 here, what I'll get? I'll get f of x star. So the function phi coincides with f at x star. Phi of 0 is equal to f of x star. Now take a very small neighborhood around 0, and that is a neighborhood taken with this increment h. So I am looking at the small neighborhood h element of minus delta plus delta. Okay? So h lies between minus delta and plus delta. So f of x star plus h, where h is lying between some minus delta and plus delta, right? So in that small neighborhood, assume, just for the sake of assumption, assume that the function phi is so nice that f of x star plus h is greater than phi of h. In that small neighborhood, the functional values of f is bigger than phi of h. Obviously, phi of 0 coincides at f x star. You can understand that two quadratic curve, one slightly above the other. You can just draw it. Now, once this is there, assume the situation where f dash x star equal to 0, that is x star is the critical point, and f double dash x star is strictly greater than 0. Now, observe that if you take the derivative, if you take the second derivative of phi of h, you will get f double dash x star. Here, if you take the second derivative of phi of h, you will get f double dash x star, right? This half will cancel with the derivative of, and you take the derivative of h square. So now, if I take phi of h, phi dash of h, what I'll get? I'll get f dash x star plus half of plus f dash x star h. Now when I put h equal to 0, I have f dash x star. So phi dash of 0 is actually f dash x star, and if f dash x star is equal to 0, phi dash 0 is 0. Now what is phi double dash 0? Phi double dash 0 is also f dash x star, and that is strictly greater than 0. So what we have learned from the quadratic function, that this a, which is half of phi dash x star, is strictly bigger than 0. So what we have learned about the quadratic function from just a few minutes before, we can now say that phi of h is strictly bigger than phi of 0 when h is not equal to 0, because now it is h0 is a strict global minimizer. Okay, it doesn't matter. We have taken h to be minus delta to plus delta. These two for every h. So for h in minus delta plus delta also this is true. So phi of h is strictly bigger than phi of 0, which is equal to f of x star. So now that shows that for any h not equal to 0 but it is lying in minus delta plus delta, we have phi of fx star plus h is greater than phi h, which is strictly greater than phi 0, which is equal to fx star. It can be rephrased as follows. So whenever x is in that interval x star minus delta to x star plus delta, and whenever x is not equal to x star, I have fx is strictly greater than fx star, which means x star is a strict local minimizer. So this condition f double dash x star strictly greater than 0, when it works, when it essentially works in the sense when this quadratic approximation of the function f, the function phi, actually locally underestimates the function f. When the function phi is locally underestimated by the function function f is locally underestimated by the function phi, then any point which has satisfied f dash x star equal to 0 and f double dash x star strictly greater than 0 will actually give me a minimizer. So what actually happens, this is the mechanism of actually getting the local minimizer, that locally your quadratic function, actually essentially your quadratic minimization is going on. So your quadratic approximation has to in a small neighborhood lie below the original function, and then only you get a strict local minimizer. The geometry is actually like that, but actually you don't really have to bother about quadratic approximation. You can, using some limiting procedure, show that if I just know that f dash x star is equal to 0 and f double dash x star is strictly greater than 0, I can show that there is a local minimizer. But what actually happens around the curve geometrically is this idea of local underestimation. So with this we will end our talk, and we will go to functions of derivatives of functions of several variables or derivatives in higher dimension in our next class. Thank you very much. Thank you once again.